Welcome to Conic Sections, Constructing the Ellipse. In this video, we start with a verbal description of an ellipse. We use that to draw an ellipse, and finally, we derive the equation of an ellipse. In the next video, we will use this equation to graph some example ellipses. An ellipse is defined by two foci and a constant distance. The distance is represented by the length of this string. For each point on the ellipse, the distance between the point and one focus, added to the distance between the point and the other focus, equals the length of the string. We can use the pins and the string to draw a curve through all the points that fit that description. Next, we draw coordinate axes on our ellipse. The x-axis runs through the foci. The y-axis is perpendicular to the x-axis midway between the foci. The origin of this coordinate system is at the center of the ellipse. The distance between one focus and the center of the ellipse is called c. Using c, we can find coordinates for the foci. One is at x equals c, y equals 0, and the other is at x equals negative c, y equals 0. If we pull the string to the right end of the ellipse, we can see that the string runs from the left focus to the right end and then back to the right focus. Imagine taking that last bit of string between the right end and the right focus and moving it to the left end. Then the string would go from one end of the ellipse to the other. We can confirm this by taking the string off the pins. The distance from one end of the ellipse to the other is the same as the length of the string. This distance is called 2a. It is both the length of the string and the distance from one end of the ellipse to the other end. Each end of the ellipse is called a vertex. The distance from the center of the ellipse to one vertex is half the length of the string, so it is a. This allows us to find coordinates for these two vertices. The one on the right is a0, and the one on the left is negative a0. Next, we pull the string to the top of the ellipse, directly above the center. This point is called a co-vertex of the ellipse. Since half of the string is on each side of this co-vertex, the distance between the co-vertex and one focus is half the length of the string, so it is a. The distance between the center and a co-vertex is called b. This means the coordinates of this co-vertex are 0, b, and the coordinates of the corresponding point at the bottom of the ellipse are 0, negative b. b is the distance between the center and a co-vertex, which is the end of the shorter axis, called the minor axis. A is the distance from the center to a vertex on the longer axis, which is called the major axis. Select any point on the ellipse xy. The distance between that point and one focus, distance 1, plus the distance between that point and the other focus, distance 2, must equal the length of the string. Distance 1 plus distance 2 equals 2a. Since the x and y axes are perpendicular, this is a right triangle. This means we can use the Pythagorean theorem to relate the squares of the lengths of the three sides. However, it's not quite the way we're used to seeing this relationship written. We usually say a squared plus b squared equals c squared, with c representing the longest side. In this triangle, the longest side is named a. This means we have b squared plus c squared equals a squared. We can solve this for b squared, getting b squared equals a squared minus c squared. Now we use this graph of an ellipse to help us write the equation of an ellipse. We start with the word definition to the left. An ellipse has two foci. Foci are points, and as we can see, one is at c0 and the other is at negative c0. And a constant distance, the length of the string, that's 2a. The distance between a point on the ellipse and one focus, well, that's the distance formula, so we want the square root of the sum of the squares of the difference in x coordinates and the difference in y coordinates. If our point on the ellipse is xy, that gives us x minus c squared plus y minus 0 squared as the distance between the point xy and the focus c0, plus the distance between the same point and the other focus. So our point is still xy, but our focus is now negative c0 instead of c0. This equals the constant, which is the length of the string, 2a. So we'll take that up here and write it as an equation. The one distance plus the other distance equals 2a. This equation has two radicals in it, which is a bit of a mess. In order to clean it up, we need to get one radical by itself. so I'm going to subtract one radical from each side, leaving one radical alone on the left. Then we square both sides. On the left, the square cancels the radical. On the right, we can't just square the two pieces separately. We need that middle term as well. If you FOIL it out, you'll see where the middle term comes in. So we have 4a squared minus 4a times the radical, plus the square of the radical, which is a square root. So the square and the square root cancel, and we're left with just x plus c quantity squared plus y squared. We can subtract y squared from both sides, and then multiply out the quantities x minus c squared and x plus c squared. This leaves us with several things that cancel. There are x squareds that can be subtracted from both sides, and c squareds that can be subtracted from both sides. But the 2xc does not cancel. We have a positive 2xc on the right, a negative 2xc on the left. That doesn't cancel. We can, however, bring all the 2xc terms together on the same side of the equal sign. That leaves us with 0 equals 4a squared minus 4a times the radical plus 4xc. We have 4's all the way through that, so it would simplify things to divide out the 4, and I'm also going to divide out the a, which is on 2 of the 3 terms. That leaves 0 equals a plus x over ac minus that radical. Now, we're going to do the same thing we did before, get one radical alone on one side of the equals sign. If we add the radical to both sides of the equals sign, we get the radical equals a plus x over a times c. Now we square both sides again, and now the radicals are gone, so that helps. And on the right side, we have to FOIL that out. We get a squared plus 2cx plus x squared over a squared times c squared. If we multiply out the quantity, x plus c quantity squared, we see that once again there's something that can be canceled. We have a plus 2xc on each side, so if we subtract 2xc, then those terms are gone. I'm out of space on this slide, so moving to the next page, taking that equation from the bottom of the previous page, we have x squared plus c squared plus y squared equals a squared plus x squared over a squared times c squared. Now I want to bring all the pieces that involve x and y to the left, and the pieces that do not involve x and y to the right. So we'll subtract x squared over a squared times c squared, and we'll also subtract c squared. Now I want the x squared terms to have a common denominator, so I multiply by 1, writing 1 as a squared over a squared. Then we can factor out x squared over a squared, and the other factor is a squared minus c squared. We also have an a squared minus c squared on the right side of the equals sign. If we divide all the way through the equation by a squared minus c squared, we're left with x squared over a squared plus y squared over a squared minus c squared equals 1. Now remember that right triangle that we found in the ellipse. We used the Pythagorean theorem to relate the sides to each other, but a was the hypotenuse, not c like it so often is. So we got b squared plus c squared equals a squared, or b squared equals a squared minus c squared. Well, that a squared minus c squared is what's in the denominator there under the y squared. Replacing that, we get x squared over a squared plus y squared over b squared equals 1. This is the equation of an ellipse. It should be familiar to you from pre-calculus. We can do the same thing with the foci along a vertical line instead of a horizontal line. Again, we have coordinate axes with origin at the center of the ellipse. This time the foci are on the y-axis rather than the x-axis. The distance between the center and one focus is still called c, and the length of the string is still called 2a. The longer axis, which is called the major axis, is still the same length as the string, although now it is vertical rather than horizontal. The distance from the center to the end of the major axis is still a. The end of the shorter axis, which is called the minor axis, is still a distance of a from the focus. The distance from the end of the minor axis to the center is still called b. This allows us to give coordinates to the vertices, co-vertices, and foci. We can select any point on the ellipse and give it coordinates x, y. The distance from one focus to this point, plus the distance from the point to the other focus, equals the length of the string, 2a. As before, we have a right triangle, with a being the longest side, so b squared plus c squared equals a squared. Using the same definition as before, an ellipse has two foci, which this time have coordinates 0, c and 0, negative c, and a constant distance, still called 2a. The distance between one point xy and the focus 0, c, plus the distance between the same point xy and the other focus 0, negative c, equals the constant 2a. This gives us an equation very similar to the one we had for the ellipse with the foci on the x-axis. We can do similar algebra to neaten it up, squaring both sides, canceling terms, squaring again, and ultimately getting x squared over a squared minus c squared plus y squared over a squared equals 1. Using the Pythagorean relationship among a, b, and c, we replace a squared minus c squared with b squared and get the familiar form x squared over b squared plus y squared over a squared equals 1. The first ellipse we drew had a major axis that was horizontal. From the center, the foci were equally spaced on both sides. The distance from the center to the focus we called c. The distance from the center to the end of the longer axis was called a. That's the same distance from the focus to the end of the shorter axis. And the distance from the center to the end of the shorter axis was called b. From this we got an equation, x squared over a squared plus y squared over b squared equals 1. The denominator under the x squared term is a squared. That's the square of the distance from the center to the end of the major axis, the horizontal axis. Under the x term is a denominator that gives the horizontal dimension. Similarly, under the y squared we see b squared, which gives the vertical dimension from the center to the vertex at the top of the ellipse. Then we graphed an ellipse with the major axis vertical. That ellipse had foci above and below the center rather than to either side. The distance from the center to the focus was still called c, and the distance from the center to the end of the longer axis was still called a, although this time it's a vertical and not a horizontal axis. The distance from a focus to the end of the shorter axis is also a, and the distance from the center to the end of the shorter axis is called b. From this we got an equation, x squared over b squared plus y squared over a squared equals 1. Once again, under the x we have the horizontal dimension. It's the shorter one now, which is b, rather than the longer one. But under the x we still have the horizontal dimension. Under the y we still have the vertical dimension. A is always the name of the distance from the center to the end of the longer axis, that is the major axis, whether that's horizontal or vertical. B is always the distance from the center to the end of the shorter axis, that is the minor axis, whether that's horizontal or vertical. The foci are always on the longer axis. These equations all put the center of the ellipse at the origin, at the point where x and y are both 0. We might want an equation for an ellipse with the center somewhere else. If we put the center at the point with coordinates hk, then the equation for the ellipse with a horizontal major axis is x minus h the quantity squared over a squared plus y minus k the quantity squared over b squared equals 1. For the center at hk, if the major axis is vertical, we have x minus h the quantity squared over b squared plus y minus k the quantity squared over a squared equals 1. In the next video, we will use these equations to graph some ellipses.